Okay, today we're going to start chapter 9 in the book, Periodic Properties. It's going to build off of what we have learned in the previous chapter with shapes of orbitals and quantum numbers. Joining us today to learn about periodic properties is a little myopic turtle. He's got glasses on. Okay. So, let's look at this. Electron configurations. What is an electron configuration all about? Well, it is asking where are the electrons in your atom? Which orbitals are the electrons in? And if we know the orbitals, that's going to lead us to, okay, what are the quantum numbers associated with each electron? A few principles we're going to go through. It's going to take us a while to build up all of our information so that we can do electron configurations. We're going to kind of be going through the configurations on the way. Our first principle we need to look at is the Aufbau Principle. It's basically building up. It says that as you look at the number of electrons that an atom has, and you're saying where are the electrons going to be, the electrons always fill up the lowest energy, the most stable orbitals first. So in order to figure out where the electrons are, knowing that they must occupy the most stable orbitals first, we need to look at the energies of these orbitals. Good news, remember the Schrodinger equation, H psi E psi? Well, that E is the energy of these orbitals. And yeah, we just put in wave functions into the Schrodinger equation, and we got out the energies of the electrons. Electrons are in orbitals. These are the energies of the orbitals. And we decided, well, Schrodinger, Heisenberg, they were looking at the most simple atom first, the hydrogen atom, because it only has one electron. And when they did that, when they looked at the energies of the orbitals for the hydrogen atom, here we have our diagram, lowest energy to highest energy, from most stable to least stable orbital. We find the 1s orbital is the lowest energy. Then comes the 2s and the 2p orbitals. Note the 2s and the 2p's are at the same energy. When something is at the same energy level within a quantum shell, we say they are degenerate. So there's two ways to look at this. The 2s orbitals are degenerate with the 2p orbitals, and you can also say the 2p orbitals are all degenerate. The 2p's are degenerate because they have the same energy. The 2p and the 2s are also degenerate because the 2s orbital has the same energy as the 2p's. Next up, higher in energy is the 3s, which is degenerate with the 3p's, which is degenerate with the 3d's, and then 4s, 4p, 4d, 4f. Note, this looks a heck of a lot like the Bohr model of the atom, where we have the 1s and then there's an energy gap between the 1, or n equals 1 for Bohr, and then there's an energy gap, a large energy gap between n equals 1 and n equals 2, then a smaller energy gap, 2 to 3, and even smaller energy gap, 3 to 4. Yeah, the quantum mechanic model of the atom, these energy of these orbitals, give us the same energies for hydrogen atoms as the Bohr model of the atom did, which is good because Bohr model of the atom has some good evidence. The Balmer series, you shine electricity through a tube of hydrogen and you see the electrons jumping in between the higher energies and lower energy orbits for the Bohr model, and you can calculate their energies. Based on that, quantum mechanics gave us the same energy values. All right. But then things start having issues. We have a bit of trouble with quantum mechanics, because when you look at the Schrodinger equation, it turns out The Schrodinger equation is only completely solvable. You can only exactly get the exact answer for atoms with one electron. Hydrogen atom, maybe a helium plus one ion. Those are the only things that work in the Schrodinger equation, which means you get the helium atom, all of a sudden you can't directly solve it. You cannot directly find the wave functions, the exact energies of these electrons. However, what experiments have shown is for multi-electron atoms, the energies of the orbitals and the shapes and sizes of the orbitals are very, very similar to hydrogen. We get similar answers when we look at multi-electron atoms as we do when we look at hydrogen, where we can solve the Schrodinger equation exactly. So these orbitals that we're going to discuss now technically are called hydrogen-like orbitals because, well, we don't exactly know what they are, but they're a lot like the hydrogen orbitals, and the experiments show that that is the case. But then we get into a difference. What we find with multi-electron atoms, the lowest energy orbital, the most stable energy orbital is the 1s. Next most stable orbital is the 2s. Note the 2p's are not at the same energy level as the 2s. The 2p's are slightly higher in energy than the 2s orbital is. And note, this is important when you're looking at this diagram here. This is only really true when there's an electron in the 2s. If there's an electron in the 2s, then the 2p's are higher in energy. All right, higher in energy than the 2p is the 3s. And then 3p's are a little bit higher still. But here's a big problem. Next high energy orbital after the 3p is the 4s orbital. After the 4s, then we get the 3d orbitals. Then 4p, then 5s, then 4d, then 5p, then 6s. How are you going to remember this? Because in the future I'm going to give you a problem asking what is the electron configuration of this atom, and you have to know the order of these orbitals to put the electrons in. You have to know that we start with the 1s, then 2s, then 2p, 3s, and so on. There are two main ways to get this into your head. The easiest, well, actually, to me, the hardest one, but it's the way a lot of students do it because to you, you might think it's easier, is to do this little trick here. Just make a column and write down 1s, 2s, 3s, 4s, 5s, 6s, 7s. Next to 2s, put 2p, and then go down 3p, 4p, 5p, 6p, 7p. Next to the 3p's, put 3d, 4d, 5d, 6d. Then after 4d, put 4f and 5f. A little review here. Question, we've got 2s and 2p. Why aren't there 2d orbitals? Recall when we look at the quantum numbers that if n equals 2, then the values of L are 0 and 1. L is 0 is the s orbital, L is 1 is the p orbital. Recall the maximum L value is n minus 1. So if n is 2, the maximum L can be is 1 in a p orbital. L cannot be 2 if n equals 2, so there are no 2d orbitals here. Anyhow, once you have these down, draw this little stair-step pattern here. And then at every corner of a step, you just draw a diagonal line. So this corner goes to 1s, then the next corner 2s, then the next corner 2p, 3s, 3p, 4s. Once you're done with 4s, you go to the next corner, 3d, 4p, 5s. Go to the next corner, 4d, 5p, 6s. Oh, check this out. 4d, 5p, 6s, 4d, 5p, 6s. This little diagram here, as you go through these diagonals, gives you this energy orientation. Now, why is this? I'm not really going to be testing you too much about why this is, but it is something you should know. So we'll go through it kind of quickly here. Something in the last chapter, we didn't discuss it too much, but when you look at the orbitals, what we see is even when you're looking at s orbitals that are spherical, the electron density, where you find the electrons, is not evenly smeared out. If this was our atom, it's not evenly smeared out. You see you've got areas of high electron density, low electron density, high electron density. Areas where there's low or no electron density is the node. Note, if you're looking at a 3s orbital, you've got even more of these undulations. High electron density, low, high, low, high, low, as you get further from the nucleus of the atom. And you can represent this graphically in a chart, and the best ones are these down here, where if you look at the probability, the radial probability of finding an electron means at the distance from the nucleus to going away from the nucleus, how far is that distance? We find that there's a higher probability of finding an electron here than a node where there's no probability, higher probability node, even higher probability of finding an electron out to the edge. Okay, so this is the way that the orbitals and atoms really look. We're going to need to know that because of a couple of other concepts called shielding and penetration. All right, we'll start with shielding. Say you had a 3+ nucleus here and you had 2 electrons in this orbital around this 3+ nucleus. Note, each electron is negative charged. So if you had an electron somewhere outside of that orbital, we can see that this orbital is only going to experience about a +1 charge, because this electron and this electron here, these 2 negative charges, kind of take up or neutralize 2 of the positive charges of this nucleus, leaving only 1 positive charge left over. 3+ here and 2- here means this electron out here is only really going to feel about a +1 charge. All right. These 2 electrons are shielding the nucleus from that electron. Note, but if that electron were in very close, it would feel the full 3+ charge and be very attracted to that nucleus. We call that penetration. If the electron is very close to the nucleus, if it has penetrated the orbital such that it is close to the nucleus, then it really feels more of the positive charge. All right. So now, when we look at these diagrams in relation to orbitals, what we find, if we look at the 3s orbital, this kind of purple line here, we see it's large. The 3s orbital is even a bit larger than the 3p, even a bit larger than the 3d in terms of distance from the nucleus. But we also find that if we trace it back, that this hump right here is larger for the 3s. The 3s orbital has higher electron density closer to the nucleus than the 3p's and the 3d's do. So that is our penetration. Because we have higher electron density here due to the 3s orbital, the 3s orbital is attracted, or electrons in the 3s orbital can be a little bit more attracted to the nucleus because they can get closer to the nucleus due to this penetration. Not only that, because the 3s electrons are here, it shields the 3p and the 3d electrons from feeling as much nuclear charge. Therefore, the 3p and 3d electrons are not as attracted to the nucleus because of the shielding by the 3s electrons. Therefore, they are higher energy orbitals. So that's the reason why all the n equals 3 orbitals, n equals 4 orbitals, 3s, 3p, 3ds, that's a reason why they are not degenerate, why they have different energies. And like I said, that's good to know. It's good to keep in your head, but we're not going to concern ourselves too much with that. We're going to focus mainly on, okay, let's solving some problems. What can we determine once we know that this is the case? All right. Our next topic, our next principle we need to look at is called the Pauli exclusion principle. What Pauli says is that no two electrons in the same atom can have the same four quantum numbers. Recall N, L, M sub L, and M sub S. Well, what that means, because you could have electron in a molecules, two electrons that have the same principal quantum number N, same angular momentum quantum number L, even the same same quantum number M sub L, but one could be plus 1/2 for M sub S, and one could be minus 1/2 for M sub S. What this means is all electrons are going to be paired. One spin up, plus 1/2, one spin down, N sub S is minus 1/2. Well, that's a lot to chew on. Let's look at some examples. All right, let's compare hydrogen atom versus a helium atom versus a lithium atom. 1 electron, 2 electrons, 3 electrons. For hydrogen, what is the lowest energy orbital that electron will go into? Where will we find the electron? Well, we'll find it in the 1s orbital, the lowest energy orbital. So if it's a 1s orbital, what are the quantum numbers? Well, 1s, therefore N is 1 and L is 0. If L is 0, M sub L has to be 0. And the spin, okay, I'm sorry, this is for helium. The spin for helium here is minus 1/2. For hydrogen, 1, 0, 0, plus 1/2. All right. We can draw it like, here's our quantum numbers for hydrogen, 1, 0, 0, plus 1/2. Or we can just say, our electron configuration is 1s1. This little superscript 1 tells us that we have 1 electron in the 1s orbital. We can draw it out as, okay, here's our 1s orbital, and we have our spin-up electron in it. For helium, it has 2 electrons. The first electron is the same as the hydrogen electron, 1, 0, 0, plus 1/2. The second electron then is 1, 0, 0, minus 1/2. We will indicate that as 1s2, and we can draw it like this. Here's our 1s orbital with 1 electron plus 1/2, the other electron minus 1/2. Note we cannot fit a third electron in that 1s orbital because you can only have their spin as plus 1/2 or minus 1/2. So if you had a third electron in this 1s orbital, its quantum numbers would be 1, 0, 0, and well, what would this be? Well, can't have it. You can only have plus 1/2 or minus 1/2. Therefore, a third electron cannot go in there without having the same quantum numbers, either plus 1/2 or minus 1/2 of these 2 electrons. Which means when we have lithium, the first electron is the same as hydrogen's electron, 1, 0, 0, plus 1/2. That electron's in the 1s orbital. The second electron is the down electron in that 1s orbital. But now we're done with n equals 1. N equals 1 shell can only have that 1s orbital. So the next higher energy orbital is the 2s. N equals 2. If it's 2s, L equals 0. If L is 0, M sub L has to be 0. And we have plus 1/2. The electron configuration is 1s2, 2s1. We can draw it like this. The 2 electrons in the 1s orbital, the plus 1/2, minus 1/2, and then the plus 1/2 in the 2s. Well, let's keep going. What about beryllium? Well, Be, beryllium, has 4 electrons. Well, 4 electrons, we know that, well, we're going to fill it up using the Aufbau Principle, 1s2, 2s2. And we can write it this way. The 1s has the up and down, the 2s has the up and down. Note, from now on, we're not going to really worry about the quantum numbers and where the electrons are, what the quantum numbers of the electrons are. I'm sure you could figure them out based on the last chapter, but we're just really worried about the electron configuration, 1s2, 2s2 for beryllium. All right, this leads us to our next principle, diamagnetic versus paramagnetic. All right, definitions. If something is diamagnetic, it means all the electrons are paired. You have a spin-up electron and a spin-down electron in the exact same orbital. Paramagnetic means we have one or more unpaired electrons. Let's look at boron. Boron has 5 electrons. So if we start at the lowest energy orbital, 1s2, 2s2, then we have 2p, and there's only one electron because here's our 1, 2, 3, 4, 5. Our 5th electron has to go in the 2p orbitals, which are a little bit higher energy than the 2s. When we draw out using boxes, here's our 1s with the up and down electrons, the 2s with the up and down electrons. The 2p, we're going to, since these orbitals are degenerate at the same energy, we draw all 3 of them. And note we have 1 electron spin up in that 2p orbital. So question, is boron atom diamagnetic or paramagnetic? Well, are all the electrons paired? No, we've got 1 unpaired electron, so boron is paramagnetic. Now let's look at carbon. 6 electrons, so we need to put 6 electrons in, 1s2, 2s2, 2p2. Well, here's our 2 electrons in the 1s, here's an electron in the 2s, but since the 2p's are degenerate at the same energy, the question is, which way are the electrons going to want to go in? Are we going to want 1 electron in this 2p orbital, say 2pz, and the other one like in 2px or something like that? Are both of them going to be in the same orbital and diamagnetic paired spins? One spin up, one spin down in different orbitals? Well, good news, we have another principle to memorize, Hund's rule. The most stable configuration in a degenerate subshell has the greatest number of parallel spins. That's just a long way of saying is when you put the first electron in here, spin up, the next electron will go in the next box over, also spin up. You will not get this situation. This is a higher energy situation, and this is a higher energy situation. All right. Which means carbon atoms are paramagnetic. That's how we can test for it. They're affected by magnets. Because an individual carbon atom has 2 unpaired electrons in it. If this were the case, if this were more stable, carbon atoms would be diamagnetic, but experiments show carbon atoms are paramagnetic. All right, Hund's rule. So the next element is nitrogen. And so, let's think here. Nitrogen has 7 total electrons. Recall, the 2p orbitals, with 2p orbitals, you've got 3 of them. You've got the m sub l as 0, as plus 1/2, 0, and minus 1/2. There are 3 of them all at the same energy, so we always draw those 3. But what that means is, they can fit 6 electrons total. 2 here, 2 here, 2 here, means that the p block of orbitals can fit in 6 electrons. S orbitals can only fit in 2 electrons. So we've got 1s2, all right, can draw those in there. And because it takes so long to draw both heads of the arrow like that, the 2s2 I'm just going to do our shortcut way like that, where we don't have to draw the other side of the arrow, the other little point. All right, 1s2, 2s2, 2p3. The question is, how am I going to put those 3 remaining electrons in the p orbitals? Well, Hund's rule says we're going to try to fill up the spins to get them the max number of parallel spins. So we're going to do this. 1, 2, 3. All right. And we're done. There's all 3 of them. Let's move to oxygen now. The electron configuration for oxygen, 1s2, 2s2, 2p4. Well, 1s2, 1, 2, 2s2, 1, 2. How do I put in my 4 electrons? Now, you could probably think this through and before even write anything down, have a good idea of where they go, but I am asking you, you'll thank me later, always do it this way. When you put in the 4 electrons, follow Hund's rule when you're putting them in there, and then add the extras. What I'm saying is if I have 4 electrons to put in here, I'm going to put 1, 2, 3 like that. And then the 4th one, well, I've got 1 more to put in. Where is it going to go? It has no choice but to pair up with one of these other spin-up electrons. Now you might have been thinking, well, I know I've got 4 electrons to put in, so I could have just put in up, down, up, up. Yeah, you could, but it's going to be nicer when you're working on problems where the answer might not be as quickly readily available in your head to just follow Hund's rule. 4 electrons to put in, 1, 2, 3, 4. This is down. All right. Skip fluorine, let's go to neon. Neon is 1s2, 2s2, 2p6. Well, 1s2, up, down, 2s2, up, down. How are we going to put in those 6? I recommend doing it this way. First 3 spin up following Hund's rule. 3 more to go, put in the spin down ones like that. All right. After neon comes sodium. But before we get to sodium, because we're starting to get lots of things to write down, let's look at a few things. First thing, it turns out that half-filled subshells are stable. So nitrogen here has the 2p subshell half-filled, 1 electron in each subshell. That turns out to be kind of stable. It makes a nitrogen atom a little bit more stable than you'd think it should be. Nitrogen atom's a bit more stable than oxygen atom because it's got this half-filled stable configuration. Note, neon has a filled subshell. Filled subshells are also nice and stable. And we're going to see that in the future, that anytime an atom can fill a subshell or half fill a subshell, it's going to probably do that because it becomes more stable when it does. All right. I think we're gonna, let's see, we're going a little long here. Let's end this video right here, and then we'll look at some more things on how to use the periodic table. Using periodic noble gas shortcut and the periodic table to get electron configurations. And we'll go through some examples.